All right, so now that you kind of understand the basis of electrostatics and the charges within the atom, now we need to talk about the electrostatic force because, as I've already mentioned, and you might already know, when objects are charged, positive and negative, they then exert forces on each other, and that force is called the electrostatic force. The electrostatic force, you need to know that force. So the electrostatic force is simply, as I said, the force between two electrically charged objects as a result of their charge. It is a non-contact force. It's one of the few non-contact forces that we know of, in addition to gravity and the magnetic force. You don't have to be, these two charged particles don't have to be in contact with each other to exert forces. And you've probably seen and felt that before. The interesting thing about this force is it is both attractive and repulsive, which is a little bit different from gravity, which is only an attractive force. We'll talk about that in a minute. It's both attractive and repulsive. So you might have heard this before. Like charges repel each other. Like means the same. So positives, positives, negatives, negatives. Unlike or opposite charges actually are going to attract each other. So let's say I have these combinations, two positives, two negatives, and a positive and a negative. See if you can determine, should be real easy, what these combinations do to each other. They're going to attract or they're going to repel. Pause the video. All right, should be fairly easy to see based on what we just said. Like charges repel, opposites attract. So the positive and positive, they're going to repel each other because they are like charges. Same thing with the two negatives. Doesn't matter whether you have negatives or positive. If it's the same charge, they repel each other. But the negative and the positive, they will attract each other. So like charges repel, same charges repel, opposite charges attract. Very, very similar concept. All right, so I mentioned that it's a non-contact force, right? Well, the other non-contact force we've talked about already is the gravitational force. I think it's really important and interesting to compare and contrast these two forces, the electrostatic force and the gravitational force. So, as a comparison, both are non-contact forces. You don't have to be in contact with the Earth to be affected by gravity, and two charged particles don't have to be in contact with each other. And they're also similar because they have identical equations because they're non-contact forces. So here's the equation we talked about a long time ago for gravitation, and this is the equation I'm going to introduce to you in just a minute for the electrostatic force. Notice it's the same thing. The only difference is G was the electrostatic constant, or sorry, the gravitational constant. K is the electrostatic constant, but it's still just a constant. It's just a number that doesn't change. Gravitational force is based on the product between two masses, the multiplication of two masses. Well, now instead of masses, Q is going to be charge. We're talking about multiplying two charges together. And then R will be the distance between the two. We're going to change the R to a D actually for the electrostatic force, but the distance between the two, and that distance is squared. It's the identical same equation, except instead of mass, we've traded it out for charge, and we've got a different constant in there for gravitational force and electrostatic force. So they're similar forces, but they're different because, number one, the gravitational force is based on mass. Mass alone, not charge, not magnetism, not anything else. It's based on mass, and it's only an attractive force. You've never ever been repelled away from the Earth because of the force of gravity. Conversely, the electrostatic force is not based on mass. It's based on charge. It's based on the charges of the two objects, those positive and negative charges, and it can be either attractive or repulsive based on the previous video. Like charges repel, opposite charges attract, right? So here's a picture of an attractive force. These paper bits are being attracted to the balloon. And here's a picture of the repulsive type of force, hairs repelling themselves away from each other. So that's gravity and electrostatic force compared and contrasted. The question is, which force do you think is stronger? Take a guess. What do you think is stronger? Is the gravitational force stronger, or is the electrostatic force stronger? Think about that for a minute and pause the video. All right, hopefully you've come to a decision. Let's answer the question, but I'm going to let you answer the question by watching this video. Rubbing the styrofoam plate with a cloth, and you should have the answer right now. In 5 seconds, we beat the gravitational force by simply rubbing the styrofoam plate with a cloth. That rubbing of the plate charged the plate. It gave the plates charges, and they have like charges, so they're repelling each other. So we just learned, you just saw evidence of the fact that the electrostatic force is stronger than the gravitational force. It took us about 5 seconds to beat the gravitational force because that plate was hovering above the lower plate. So the electrostatic force in that case won out. And it's actually a much stronger force. Well, why is that? Well, the short answer is it has to do with their constants. It's a lot more than that, but their constants, those two constants we talked about earlier, they give us some evidence of that. So let's look at the constants. You might remember when we talked about gravitation, Newton's universal gravitation constant was this, 6.67 times 10 to the negative 11th. When we write that out in regular notation, it's 0.000, that's 10 zeros and 667. That's a stinking small number. That's a really, really small number. And again, it goes right here in the equation. It incorporates in. Whereas the electrostatic force constant, K, is a different number. 9 times 10 to the ninth. This is a negative exponent. This is a positive exponent. 9 billion is what that is. 9 with 8 zeros behind it. 9 with 9 zeros behind it, sorry. So obviously that's a really big number. Ridiculous amounts. Like it's not even a comparison to say that this is bigger than this one. The electrostatic force, here's the point, is 10 to the 20th or 100 quintillion times stronger than the gravitational force. Now, to some of you that might surprise you because many people think initially that the gravitational force is stronger. And some of that reasoning is along the lines of, you've been hurt by the gravitational force before. You've fallen. Gravitational force is strong enough to keep entire planets in orbit. That's got to be a strong force. But when you think about it, there's also a gravitational force between you and the person that might be sitting next to you, but you've never felt it. And the reason you've never felt it is because mass for mass, the force is so very small. You have to have a mass the size of the moon to really be able to see the gravitational force. Whereas, like in the video you just saw, we don't have to do very much work at all to observe the electrostatic force. It's a very, very strong force per charge. So the electrostatic force is actually much, much bigger than the gravitational force.